Alright, hi. Alright, let's get back to one. Non-resident training course, Navy Electricity Electronic Training Series, Module 9, Introduction to Waves Generation and Wave Shaping, Navy NAVEDTRA 14181, approved for public relation distribution unlimited. Chapter 3, Part 2. Alright, blocking oscillator applications. Basic principle of inductance is the increase of the current through the coil is a linear, that is, the rate of the currents increase with the constant with respect to the time the induced voltage will be constant. This is true with the primary and secondary transformer, figure 332, with a V with a V show of the voltage waveform across the coil through the current coil when the current through the increase of the constant rate. Notice that the waveform is similar shape of the trigger pulse as shown in figure earlier in figure 3.1 view E. By definition, a blocking oscillator is a special type of oscillator which uses inductive regenerative feedback. The output derivation frequency of such pulses determined by characteristics of the transformer in relationship to the circuit. The figure 333 shows the blocking oscillator. This is simple form to use the illustrated circuit operation. Figure 324 B shows the voltage across the coil. Voltage of the inductive voltage. Also 333 blocking oscillator and transformer emitter going to the ground, collector going to the transformer winding 1 and 2, induction winding 1 and 2, transformer tapped, voltage current collector, capacitor and resistor. When the power is applied with the circuit with the resistor 1 provided with the forward bias with the transistor 1 conducts current flow through the transistor 1 primary to the transformer winding 1, induces the voltage of the inductor 2. The phase tap of the transformer indicates 180 degrees phase shifting. The bottom of the side of the inductive 1 is going negative, the both side of the inductive 2 is going positive. The positive voltage of the inductive 2 is coupled with the base for the transistor through capacitor 1 and transistor 1 conducts more. This provides more current collector current, more current through inductor 1. This action regenerative feedback very rapidly sufficient voltage to apply with the saturate the base for the transistor 1. Once the base becomes saturated, it loses control over the collector current. The circuit now can be compared to small resistor transistor 1 series, the relatively large inductor, or in a RL circuit. The operation of the circuit has the point of the generator with a very steep leading edge for the output pole. The figure 334 show the idolized collector with the base waveforms. Once the base for the transistor 1, figure 333, becomes saturated with the current with the increase of the inductor 1, determine the time of the constant of the inductor 1. The total series resistance from time 0 to time interval 1. Figure 334 cover the current increase now shown approximately linear. The voltage of the cost inductor 1 will be constant values along with the current increase through inductor 1 and is linear. Figure 334 shows the blocking oscillator ideal waveforms. Collector waveform for voltage current collector timing 1 and 0, 2 and 3. Overhead base waveform. At time 1, the inductor the inductor 1 saturated at the time. There's no further change of the magnetic flux, no coupling further with the inductor 1 and inductor 2 capacitor will have charge during the time 0 to time 1. Will now discharge through resistor 1 cut off of the transistor 1, collect for the current through the stop of the voltage across the inductor 1 returns to 0. The length between time 1 and time 0 and time 1's interval in time 2 and time 3 is the next step of the pulse width, which demands mainly with the character of the transformer. The point over which the transfer saturated the transformer is chosen that will saturate about 10% of the total circuit current. This ensures that the current increase with the linear transformer control of the pulse width because it controls the slope of the current collector current increase between the time 1 0 time 1. Since the total time collective is equal to and TC is equal to inductive divided by resistor. The greater the longer the time current, the time constant is equal to the induction over time divided by the resistance. The longer the time constant, slower the rate of the current increase. The rate of the current increase is slow. The voltage of the inductor 1 constant for the large time. The primary determines the pulse of the width. From time 1 to time 2, the transistor 1 is held at the cutoff by capacitor 1. Discharging through resistor 1, figure 333, the transistor is now said to be black with capacitor 1 gradually loses charge of the voltage on the base of the transistor 1 in terms of the forward bias condition. Transformer 2, the voltage for the base has become sufficiently positive for the forward bias for the transistor 1. The cycle is repeated. Our collective waveform may have an inductive overshoot with a parasitic oscillation at the end of the pulse. The transistor 1 cuts off the current with the inductor 1 ceases, the magnetic field collapses, induces a pulsing positive voltage of the collector of the transistor when the oscillations are not desirable. Some of the means must be employed to reduce the transformer. Primarily, many designs have the high DC resistance resulting in low merit. The resistance will decrease the amplitude of the oscillation. However, the more damping necessary for such a low merit transformer, primary alone can achieve that. If so, damping resistor can be placed in the parallel inductor 1 with inductor 1 as shown in figure 335. Figure 335 shows the circuit damping resistor 1, voltage current collector, emitter base, ground, transformer tapped, 180 degrees, inductor 1, inductor 2, capacitor 1, resistor 2, rheostat, output grounded. Where the external resistance is placed across the tank of the formula of the mirror of the tank circuit of the mirror is equal to the resistance times the capacitive inductance. Where the inductance reactance. The mirror is equal to the resistance times the inductance reactance. The resistance is equal. The resistance is the equivalent total circuit of the resistance in parallel with the inductor with the inductor. You should be able to see that the equation for the mirror is directly proportional to the damping resistance. In figure 335, the damping resistor of the resistor 2 is equal to the show that the mirror which reduced the amplitude overshoot with the parasitic oscillation. Resistor 2 is varied from infinity towards 0 to decreasing resistance will lower the transformer to the point with the pulse amplitude, pulse width, and pulse repetition frequency are affected. If the phase repetition is affected, phase repetition frequency are affected. If the reducing of the oscillator will achieve the function by varying resistor 2 varying the degree of the damping can be achieved in 3 ways, of which they're shown figure 336 view A, view B, and view C. Figure 336A shows the waveforming damping critical damping, and then figure 3336B show the waveform damping, under damping, overshoot, and then over damping waveform, figure 336. Critical damping can give it the most rapid response without overshoot. This is accomplished by adjusting resistor 2 for the achieve of the waveform shown figure 336 view A. The resistance of the resistor depends on the mirror of the transformer. The view A show the oscillation include the overshoot and the damping out. Under damping give the rapid transient response of the overshoot caused by the high or an infinity resistance is shown figure 336 view A. View B, over damping is called with a very low resistance. Give the slow resistant response. It must reduce the pulse amplitude shown figure 336 view C. The blocking oscillator discovered the free running circuit is fixed and the phase repetition frequency. Some of the means of the stabilization frequency is needed. Our methods apply external synchronization triggers figure 337 of view A and view B. The coupling capacitor C2 feeds the input synchronization trigger to the base of the transistor 1. Figure 337 basic oscillator synchronized. Inputs go through capacitor 2, resistor 1, capacitor 1, induction coil 1, and transformer iron core L2 and L3. Tertiary output, voltage current collector, emitter, grounded. Input triggers are phase rate, time 400 microseconds phase rate, and time for 200 microseconds base waveform, output waveform, time 0 to time 1, time 0 to time 1 to time 2. If the trigger frequency is made slightly higher than the free running frequency, the blocking of the oscillator will lock in a higher frequency for instant. But they assume with the free running of the frequency of the blocking oscillator at 2 kHz of the phase repetition time, 500 microseconds of the sync pulse will at the phase repetition time of 400 microseconds, 2 kHz are applied with the base blocking oscillator will lock in and run at 2.5 kHz to synchronize. If you sync the phase resistance time. Phase repetition time is too high, however, the frequency discovered, the frequency division will occur, but this means that is in sync of the phase repetition time is too short. Some of the triggers occur with the base far below the cutoff. The blocking oscillator may then synchronize with every second and third pulse. For example, 337 view A and view B, the trigger pulse is applied with every 200 microseconds or 5 kHz. The trigger appears to be at time 1 interval. It is not sufficient to amplify to overcome the cutoff bias of the turn on transistor 1. At T2, the capacitor of the capacitor is now in discharge of the trigger with the transistor 1 to the conduct. Note that the 200 microseconds the input trigger with the output of the phase repetition time of the 400 microseconds the output frequency of the 1/2 of the input trigger frequency and blocking oscillator becomes the frequency divider. Are your time-based generators. Radio oscilloscopes, computer circuits are all of the Sawtooth voltage current waveforms. The Sawtooth wave shape must have the linear rise. The Sawtooth waveform is often used to provide uniform progressive movement of an electron beam across the face of the electrostatic cathode ray tube. This movement of the electron beam is known as sweep. The voltage will cause the movement and it is known as the sweep voltage. Circuit will produce the voltage sweep generator with a time-based generator. The most common type of the time-based generator is developed in the Sawtooth waveform by using some type of the switching action with either charge or discharge RC and RL circuits. Alright, your Sawtooth wave. The Sawtooth wave can be generated by using an RC network, possibly simple as Sawtooth generation, in which is shown figure 338. View A. Assume that the time interval T0 view B with switch 1 is placed in the position P. The instant the switch closed, the applied voltage appears at the resistor and capacitor begins to charge at the voltage A through the resistor. The remainder of the closed long enough, the capacitor will fully charge over the applied voltage. You should remember that the Neets module 2 alternating current transformer of the capacitor of the time 5-time constant. Fully charged, the capacitor charge with the applied voltage. The rate of the charge followed the exponential curve of the linear voltage. The desire for the full charge of the capacitor cannot be used because of the exponential curve between it becomes non-linear during the first time constant. Alright, so you have your voltage. Applied voltage at 100 volts of the resistor at 100 kilo ohms. The capacitor at 0.01 microfarads. Q going to the ground. P connecting the circuit in switch 1. Series RC circuit. Figure 338 series RC circuit at 10% of or less of the applied voltage to the time 0 interval applied voltage 5-time constant. 1/10 of the time constant or less. However, during the first 10% of the first time constant of the rate of the voltage change of the cross of the capacitor almost constant and linear. The summertime with the switch 1 placed in the position P with the time interval 0. Capacitor is allowed to charge for the tenth of the time constant with the shown with the time interval 0 to T1. In view B with the note for the rate of the voltage change of the cross of the capacitor nearly constant over the time 0 to time 1. Now assume that T1 time 1 is the switch is moved with the position of the to P to position Q. Short of the capacitor discharge very rapidly. The switch is placed back in the position P, but the capacitor will start to charge again. By selecting the side of the R and C, that you can now have the time constant any value you desire. Further controlling the time switch 1 remains closed. You can generate the Sawtooth with any duration. Figure 339 is a universal time constant chart. Note that the chart with the 1 time constant and 1000 microfarad switch 1. Figure 338 view A can be closed no longer than 100 microseconds to obtain reasonable linear Sawtooth. An example, the capacitor 1 will charge with nearly 10 volts at in 1/10 of the times the constant. Alright, this shows your time and time constant 0 to 1, 0 to 1 through 5% of the voltage current, 10 in percents, 10%. Is the capacitor on voltage, the RC circuit, the inductor current with the resistor voltage on buildup, and B would be your capacitor voltage on discharge, resistor voltage, capacitor current on charge or discharge, inductor current or resistor voltage on decay, inductor voltage on buildup or decay. The dimension of the Sawtooth waveform, the use of the oscilloscope needed to discuss before, but going any further. Figure 340 shows the Sawtooth waveform, the various dimensions label the duration of the rise of the fall voltage of T0 to T0 to time interval T0 to 1. You know the sweep time electrical length of the electro beam of the oscilloscope, the move across the face of the cathode tube during the sweep time. The amount of voltage rise per unit of the time is referred to as the slope of the waveform. The time from the T1 to T2 is capacitor discharge time that's known by the full time and the flyback time. This discharge time that's known as the flyback time is because during the period of the electro beam return to the flies back in the end of the scanning at the end to begin with the next line. Alright, figure 340 shows the Sawtooth waveform time, linear slope, sweep time, electrical length, phase readiness time. Frequency is equal to 1 over the phase readiness time, time interval 20 to T1, 21 to 2, fall time, amplitude of physical length. Amplitude of the rise of voltage known as the physical length is called the physical length because of the greater the peak voltage of the greater physical distance the peak will move. Or the example, the amount of voltage needed to move with the electron beam 4 inches with the twice the amount of the need to move the beam 2 inches across the face for the given of the cathode ray tube. Voltage rise between T0 and T1 of the linear slope of the wave. Linear rise with the voltage determine the amount of the time of the capacitor to allow for the charge. If the charge time is kept short, 10% less of the 1 time constant, but the linear is responsibly good. As stated, the discussion time-based generator of the waveform produced any saw wave generation must be linear. Linear sawtooth is one with the equal change of the voltage with the equal change in time. Refer to the universal time constant chart figure 339. You can see that the most desirable charge curve is first 1/10 of the first time constant. Figure 341, view A with the transistor sawtooth generator figure. In this figure, resistor 1 forward bias with the resistor for the transistor 1, capacitor 1, coupling capacitor, transistor 1 serving as a switch in the RC network, consisting of the resistor 2 and capacitor 2. The forward bias with the transistor 1 generates conduct the saturation collector voltage. The output near 0 volts, indicating the waveform. In the view B, the charge felt with the capacitor when it's nearly 0. A negative gate is applied with the transistor 1 with the cutoff of the transistor 1 allowed with the capacitor 2 to charge. Length of the time that the gate is negative is determined if the transistor 1 will remain cut off. If in turn, however, how long the capacitor 2 will be allowed to charge, the length of the time the capacitor 2 is allowed to charge, referred to with the electrical length of the sawtooth that is produced. Alright, figure 341 shows the transistor sawtooth generation input going through capacitor 1 and resistor 1, resistor 2, 5K, emitter going grounding, collector going in voltage, current collector 30 volts, output sawtooth, capacitor 2, microfarads, input gate 700 microseconds, 500 microseconds, 200 microseconds cutoff, output voltage 3 volts, and chime 1 and 2 show the drop, the sawtooth amplitude. The amplitude of the sawtooth that produces the limited value of the voltage current collected with the U. The circuit, for example, the voltage of 30 volts of the capacitor is allowed with the charge of the 10% of the 30 volts. The amplitude of the sawtooth of the 3 volts of the voltage current collector increases to 40 volts of the capacitor to charge of the 10% of the 40 volts. The output will increase the amplitude of 4 volts charging the value of the voltage current collector. The circuit change the amplitude of the sawtooth waveform from its produced amplitude to determine the physical length of the number of the time constant U. The circuit that has not been changed linear does not change the voltage current collector. Linear slope of the produced circuit is dependent on two variables: the time constant of the resistor RC circuit of the gate, the length of the applied by the circuit. Unto the circuit will produce the linear sawtooth shape of the components selected are such that only 1/10 of the one time constant left is U. The K length is the amount of the time the gate is applied by the circuit. The control of the time of the capacitor is allowed to charge. The value of the resistor 2 and capacitor terms determine its time for one time constant. T's time constant is equal to the resistor constant, identified with the number of the time constant for the fraction of the 1 TC is divided in the time constant with the time the capacitor is allowed to charge. The number of time constants is equal to the gate length over the time constant. In figure 341, the gate length of the 500 microseconds and the time constant is produced. And resistor 2 is 5 kilo ohms. Capacitor 1 is 1 microfarad with the number of the time constants computed is followed. 500 times 10, 6, negative 6, 10 to the negative 6 per seconds, 5 times 10 to the third, 1 times 10 to the 6 microfarads. You get 1/10 of the time constant. Therefore, the time constant length of the time required with the length rise of the sawtooth waveform, the formula over the time constant of the gate length over the time constant. Alright, it shows that increase the gate length with increase the number of the time constant, increase the number of the time constant, decrease the linearity of the region of the capacitor to natural of the great of the percent applied voltage portion of the charge curve that is being used as less linear. The waveform is figure 342 for the view A show the increase the amplitude physical length with increase the time of the capacitor 2 is allowed with the charge of the electrical length. The decrease in linearity is a small percent of the voltage current collector energy for the gate length that decreases. As shown in view B, the decreased gate length that result of the increase in the linear decreasing the time of the capacitor 2 is allowed with the charge of the electrical length decreasing the amplitude physical length. Alright, 342 show the relationship of the gate linearity, linear slope time, A, the amplitude of the gate, and the increase of the gate length. The 342B show the relationship of the gate linearity, the decrease of the gate length, the linear slope, the amplitude, the time, and changing the value of the resistor and the capacitor of the circuit affects the linearity sent to the control of the time and one time constant. For example, the value of the capacitor 2 with the increase of the circuit is shown for the figure 343 with the UA time for time 1 constant, increase of the number of the time constants will then decrease of the decreases the number of the time constant linear, increase of the region for the small percent of the voltage current collector is U. The circuit is operating with a more linear portion of the charge curve with the increase of the value of the time constant. The capacitor 2 and resistor 2 decrease the amplitude of the sawtooth physical length this because of the capacitor 2 now charged with a smaller percent of the voltage current collector given in total time electric length will remain the same between the because of the length of the time that the capacitor 2 is allowed to charge that has not been changed. Alright, figure 343 shows the resistor and capacitor to linearity of the gate, the increase of the resistor capacitor linear slope, amplitude, and time. This shows the relationship of the resistor and capacitor in time, decreasing resistor and capacitor in time or linear slope, amplitude, and time in the gate. Decrease the value of the time constant of the resistor 2 and capacitor 2 or capacitor 2 shown for the 343 view, but the result of the increase of the number of the time constant, therefore the linear decrease of the any time of the number of the time current constant, increase the percent of the charge, increase the universal time constant, chart figure 339, amplitude, physical length, increase the gate length of the time of the capacitor 2 is allowed, the charge of the through resistor 2 remains the same, therefore the electrical length remains the same. Linearity is affected by the gate length value of the resistor value of the capacitor, not affected by the change of the value of the voltage current collector. Increase the gate length with increase the linearity, decrease the gate length with increase the linearity, increase the resistor or capacitor, and circuit with increase the linearity, decrease the resistor or capacitor, circuit decrease the linearity. Alright, the entire time the Sawtooth at the time of the capacitor begins charging the time interval time interval 0, the figure 341 view B of the time when it starts charging the time 2 is known as the pit. Phase readiness time of the wave, phase repetition of the wave, the pulse with the repetition frequency of the Sawtooth wave is phase repetition frequency is equal to 1 over the phase repetition time, and junction Sawtooth generator. So far, you've learned that the chapter of the switch with the resistor capacitor can generate with the Sawtooth waveform when using the unijunction transistor switch with the simple Sawtooth generator looks as the circuit of figure 341 view A, the output wave shown with figure view B. You want to review the unijunction transistor Neets module 7 and introduction solid-state devices power supply chapter 3 before continuing. Or your schematic, the grounding capacitor 1 microfarad, resistor at 25 kiloohms, the 200 volts out of the base 2 and base 1 grounded emitter going to the base transistor 1. When the 20 volts is applied with the base 2 and the base 1 with the negative type of the bar with the voltage of the divider with the volt over the 12.8 volts appear with the point near the emitter, the first instant of the capacitor 1 has no voltage across the output of the circuit has taken across the capacitor 1 with the equal of 0 volt. The voltage across the capacitor 1 is also the voltage applied with the emitter of the unijunction. The unijunction now reversed by after the time 1. Time 0 with the capacitor became the charge of the door 20 volts. The time 1 with the voltage across the capacitor voltage with the emitter reached with approximately 12.8 volts. With the peak of the point with the unijunction now became the forward bias with the emitter. Forward bias with impedance become between the emitter and the bias. Base 1 is just the few ohms. Similar to placing a short across the capacitor discharge very rapidly low resistance of the base 1 to the emitter. Capacitor 1 charge of the discharge of the voltage of the emitter of the base 1, also the creep of the transistor with the continue with the flow with the bias and along with the voltage of the capacitor 1 is larger than the valley point of the unijunction. At time interval 2, the 3 volt valley point of the unijunction has reached the emitter now becomes reversed by the impedance of the emitter of the base 1, return with the high value of the immediate after the time 2 of the transistor 1, reversed by the capacitor charge with approximately 3 volts. Capacitor 1 now starts with the charge toward the 20 volts that it did originally just after time interval time constant 0. This is shown in time and time constant 2 to 3. Figure 344 view B. Show the 344 unijunction Sawtooth emitter waveform, peak point, valley point, time is interval 2 to 1 to 2 time 1 to 2 time interval 2 to 3 time 4 12.8 volts microseconds and fives. The circuit operation for now on is just a continuous repetition axis between the time interval 2 and 4. The capacitor charge with the emitter will become with the forward bias of the unijunction can conduct with the capacitor when discharge of the transistor 1 becomes reverse bias of the capacitor 1 again starts the charging. Now let's determine the linearity and electrical length amplitude of the output waveform. The first linearity charge of the circuit of the volt 20 volts below time 5 time constant for the circuit shown in figure 344 view B. Capacitor 1 is allowed to travel the time interval 2 and 3 with the defined with the percent of the charge using the equation. Percent of the charge is equal to the voltage peak minus the voltage voltage valley over the voltage amplitude minus the voltage valley times 100, where you get 57%. This works out to be 57% far beyond the 10% required for linear sweep. The voltage linearity is very poor in this example. Electrical length sweep time is measured for the time constant 2 and 3, which can be found with multiplying resistor capacitor time with the number of the time constant. To refer to the universal time constant chart again with the find with the 57% of the 0.83 time constant multiplying 0.83 time resistor 1 capacitor 1, you will find the electrical length with approximately 21 milliseconds. Electrical length is equal to resistor times the capacitor resistance time the capacitation times the number of the total contents. You get 21 milliseconds. Physical length of the amplitude to determine the subtraction valley point with the peak time with the 9.8 volts. In the example, the 12.8 volts to minus 3 volts. The sweep generator produces the more linear output solid waveform referred to the circuit in figure 345 UA. Resistor 1, capacitor 1 for the RC time constant over the capacitor charge toward the 34 volts in the circuit. 34 volts, 345A, improve the unity junction in Sawtooth generation voltage, 35 volts, resistor 1, 300 kilo ohms, output, capacitor 1, 5,000 of the microfarad, voltage, voltage by or base, base 1, resistor 2, base 2, base 1, resistor 3, emitter, voltage peak valley. The output waveform shown in figure 345 UB, lower voltage applied with the B1 to B2 with the peak valley points for the close together, calculating percentages. Percentage of the voltage equal to the voltage, primary minus the voltage, A voltage, okay. Linears cover the universal time constant, 10% of the charge about amount of 1.10 of the time constant electrical length of the RC time, the number of the time constant width of the resistor 1, 300 kilo ohms capacitor, 5,000 microfarad, the time constant of the 1500 microseconds, 1/10 of the time constant, 150 microseconds electrical length of the 150 microseconds. Phase repetition time is the electrical length plus the fall and flyback time of the capacitor 1 is discharge of the 5.3 volts of the 2 volts and 15 microseconds. Phase repetition time is 150 plus 15 or 165 microseconds. Phase repetition frequency is about 6 kilohertz. Phase repetition frequency is equal to 1 over the phase repetition time. Some of the union junction circuits are triggered to obtain the very stable phase repetition frequency. One method is applied with the trigger with the B2 for the shown with the gear 340 with the trigger with the applied with the B2 reduce the internal base voltage enough to cover the forward bias of the condition emitter circuit that cover the cutoff sweep of the cloud with the capacitor 1 discharge through B1 to the emitter circuit. This capacitor 1 reach over the next circuit arrive with the capacitor 1 discharge of the circuit operation parameters are figured with the, in the same manner the previous Sawtooth circuits. Figure 346 shows a synchronized Sawtooth generation. Resistor 1, capacitor 1, resistor 2, resistor 3, bias B1, B2, MIE, emitter, capacitor 2, input triggers time 1 and time 2. Her transistor Sawtooth generation. Next Sawtooth generation are U of the conventional and positive negative power of the transistor shown figure 347 of U A of the generation U of the RC network. The transistor provides a switching action. 347 of the transistor Sawtooth with the positive negative power of the transistor. Input capacitor resistor 15 kilo ohms grounded on the emitter section 1 microfarad circuit and the resistor 3 5 kilo 220 volts output. Waveform circuit shown view B and view C with the MO input with the transistor 1 base near the saturation resistor 1 voltage of the capacitor 1 and low with the 2.5 volts because of the low resistor 3 drops most of the applied voltage of the transistor must become off cut off allow the capacitor 1 and sharp with the cut off of the transistor 1 and the power of the rectangular wave is used. 347 of the transistor Sawtooth generation positive negative positive input generation 700 microseconds 500 microseconds 200 microseconds cutoff. 347 the transistor Sawtooth generation positive negative 2.25 volts output. Since the transistor 1 positive negative the transistor positive voltage may be U with the driver. The cutoff of the figure 347 is UB with the drove of the rectangular wave of the 500 microseconds along with the power of the alteration time interval 0 with the power of the gate applied with the base of the transistor 1 cuts off the transistor 1 effective remove the transistor from the circuit that opens the switch. Capacitor 1 shove of the resistor 3 towards 20 volts starting the charge of the negative 2 volts over the time 1 2 capacitor 1 time 0 to time 1 500 microseconds to 425 negative 425 volts time resistor 1 let's determine the percent of the charge. Alright, your percentage of the change volts of the capacitor 1 over the voltage capacitor minimum voltage current collector minus the voltage of the capacitor minimum times 100, 10%. Increasing the resistor of the 3 with the capacitor 1, increasing the time constant of the capacitor will now travel the high voltage of the same period of the time, decreasing the width of the gate with the maintaining the same time of the constant to prevent the capacity of the charge as much as less of the on the capacitor of the same voltage applied linear has been improved. Decreasing the resistor 3 capacitor or capacitor 1, increasing the gate width of the decreased linearity, changing the applied voltage will change with the charge of the capacitor. The percent of the charge remains constant, however, that does not affect the linearity. Alright, T1 part of the alteration input gate ends with the transistor 1 represent for the forward bias condition of the transistor near saturation very low resistance capacitor 1 discharge rapidly with the time interval 1 and 2 as the shown figure 347 the view C with the capacitor discharge in less than 200 microseconds. The length of the negative alteration of the gate. The negative gate is made longer on the discharge time of the capacitor initial of the circuit is returned with the original condition time interval 1 and 2 for the capacitor discharge of the circuit returns original condition ready for the another part of the gate to arrive the next part of the gate arrive the time interval 2 the action repeats. The amplitude of the output Sawtooth wave is exactly 1.75 volts, or 4.25 volts, and minus 2.5. The electrical length of the same, and the positive alteration input gate of the 500 microsecond phase readiness. Phase repetition time is 500 microseconds. The phase repetition frequency is 1 over the phase repetition time, 1,428 hertz. Your trapezoidal sweep generator normally oscillate with the synchroscope of the electrostatic deflection, also of the name, then applied with the electrostatic field move with the electron beam. The need here the Sawtooth voltage waveform. Another method of electron beam deflection, electromagnetic deflection current through these coil to produce the electromagnetic field for the position of the beam electromagnetic system requires the Sawtooth current with increased linear voltage because of the inherent characteristic of the coil. The Sawtooth voltage does not cause the linear increase of the current. The linear increase of the current voltage of the trapezoid voltage waveform applied to the coil. This section discusses the generation of trapezoidal wave. Alright, 348. The show of the trapezoidal wave of the wave consists of the sharp of the almost instantaneous jump in the voltage followed by the linear rise of the sum peak of the value of the initial charge of the change of the voltage at the time interval 1 is called the jump or step. The jump is followed with the linear Sawtooth voltage rise. The time of the jump to the peak of the amplitude, sum of the voltage pump to the Sawtooth peak, where the peak of the value of the curves and the electrical length of the peak voltage amplitude is sum of the jump voltage and the Sawtooth peak voltage waveform is shown in considerable combination rectangular wave and then Sawtooth wave. Show the jump electrical length, linear slope of the physical length, trapezoidal waveform. Inductance and resistance of the coil of the distribute the RL circuit. The voltage drop of the coil of the inductance resistance must be added to obtain the voltage waveform and produce the linear rise in current. The linear rise of the current produces the linear rise of voltage across of the resistance of the coil and constant voltage drop across of the inductance of the coil. Assuming that figure 349 view A represents the deflection coils, if you apply with the voltage wave shape to the circuit, the will drop of the square wave across the inductor L, Sawtooth across the resistor R, then the linear current will result in 349 series of the L and R circuit, the voltage of the inductor and resistor. View B349 show the waveforms of the voltage applied on the square wave. The recall of the inductor, the active, the open circuit of the first instant of the current now start with the flow with the develop of the voltage across the resistor, the square wave of the amplitude, square of the wave applied with the voltage across the inductor start with the drop, and assuming that the voltage appeared with the across the resistor due to the fact that the voltage across the inductor resistor must add up to the applied voltage. Alright, so you have the ampage resistors, your applied voltage inductor voltage resistor, time interval 0 to time interval 1. With the applied voltage being trapezoidal voltage, with the shown figure 349 view C, with the instant current flow of the voltage appear across the resistor applied with the voltage increase. With the increased applied voltage, and the inductor voltage remains constant with the voltage inductor jump level and current circuit current of the voltage amp the resistance of the rise of the linear rate from the jump voltage point. Now that you have added up the inductor voltage of the resistor voltage, and at the point of between the time interval and 0 to 1, the sum is applied with the applied voltage. For the key fact is that the trapezoidal voltage must be applied to the sweep coil of the coil of the linear rise of the current. Linear rise of the current will cover the uniform change of the magnetic field, which in turn will cause the electron beam to move at a constant rate across the cathode ray tube. Our view 3940 and 3349C will let the LR secret the virtual voltage applied, voltage of the inductive, the voltage resistive, amperage resistors. There are many ways that generate a trapezoidal wave shape. For example, the rectangular part could be generated in one circle with the 12-2 portion, and now with the two combined waveforms. Instead of the third circle, for easier, less complex U of the RC circuit in combination with the transistor generated trapezoidal wave shape in one stage. Figure 350 view A shows the schematic diagram and the trapezoidal generated the wave shape of the circuit is shown view B with the resistor 1 provided with the forward bias with the transistor 1 without the input with the transistor 1 conducts very hard near saturation coupled capacitor 1 coupled with the input gate signal with the base with the transistor 1 resistor 2 resistor 3 capacitor 2 formed with the RC network which formed with the trapezoidal wave. The output is taken across resistor 3 and capacitor 2. Input gate is capacitor 1 with resistor 2 and resistor 1 on the base and the collector. And then the collector also has resistor 2 and resistor 3 with the capacitor voltage current collector at 50 volts. Input gate and output trapezoid microseconds. Rectangular wave shape and then the Sawtooth. The transistor 1 conducting very high with the collector voltage with the near the zero with the prior with the gate with the been applied with the voltage across the resistor 2 is about 50 volts, which means the current flow with the cross resistor 3 and resistor capacitor 2 has no charge. Time interval 0 with the negative alteration of input gate is applied with the base of the transistor 1, driving it into the cutoff at the time of the transistor effectively removed from the circuit. The circuit is known by the RC, the network. The voltage applied with the instant of the transistor 1 cuts off the 50 volts will appear with the cross of the combination of resistor 2 and resistor 3. The capacitor being short with the first instant of the 50 volts will divide proportionally according to the side of the 2 resistor 2. Then we'll have 49.5 volts with the resistor 3. We'll have 0.5 volts with the 0.5 volts across the resistor 3. Jump resistor is applied to the jump voltage since the output is taken with the cross of the resistor 3 and capacitor 2 with the series of the output with the jumps at 0.5 volts. Observe that the trapezoidal generator is different from the Sawtooth generator. The output has been taken with the cross of the capacitor alone. The output voltage would have 0 volt at first input by splitting of the resistor with the resistor RC network. So the output is taken across the capacitor apart with the total resistance produced with the jump of the voltage. Refer again to the figure 350 view A and view B. The time interval 0 and time 1. Constant capacitor 2 begin with the torque with the 50 volts through resistor 2 and resistor 3. The time constant with the circuit is 10 milliseconds, and the input gate is 1,000 microseconds. The capacitor can charge with only 10% of the one-time constant with the Sawtooth per part with the trapezoidal wave will be linear. Time 1 input gate ends with the transistor 1. Begin with the conductive heavily with the capacitor 2 discharge with the resistor 3. The transistor 1 with the time required with the discharge with the capacitor 2 to primarily determine the value with the resistor 3 capacitor 2. Minimum discharge in circuit with 500 microseconds at 500 kiloohms times 200 of the microsecond times 5 at the time. The timing 2 for the capacitor had the discharge back to 0 volts. The circuit is quiescent with the remainder of the condition with the time 3 with another gate is applied with the transistor. The amplitude of the voltage was calculated with the, to be 0.5 volts. 2 for the portion of the wave of the linear because of the time 0 and time 1 is only 10% of the whole charge time. The amplitude of the trapezoidal wave is approximately 5 volts. The electrical length of the same with the input gate length of the 100 microseconds. 1,000 microseconds. The linearity is effective with the same manner with the Sawtooth generation. Increase with the resistor 2 or capacitor 2. Increase the gate width will improve the linearity, but the changing of the applied voltage will increase the output amplitude will not affect linearity. Alright, linearity with the trapezoidal waveform produced with the circuit is shown figure 350 view A and view B, but it depends on the two factors of the gate length of the time constant of the RC circuit. The recall there is the same factor for the control of linearity of the Sawtooth generator. The formula developed earlier, but it still remains true, but it enables to determine the effect that the factors have on linearity. The number of the time constants equal the gate of the total time constants. Increase of the gate length will result in the increase of the number of the time constant, the increase of the percent of the charge of the capacitor will during the time of the interval. As stated earlier, but the number of the time constants will exceed the 1/10 of the linearity will decrease. The reason for the decrease in linearity with the greater percent of the voltage current collector is the universal time constant chart in figure 339 show with the charge line at the beginning of the curve. Decrease in the gate length with the opposite effect of the linearity with the cause linearity to increase the reason with the increase of the small number of the time constant used in turn. Small percent of the voltage current collector is used. Changing the value of the resistance the capacitance with the circuit is also affect the linearity of the value of the capacitor 2. A resistor 3 is increase with the time and increase with the one time constant. Increase with the time constant and one total time constant result in the decrease with the number of the total constant. Number of the time constants required with the goal of the good linearity. As stated earlier, the decrease with the number of the time constant result in increased linearity with less than 1/10 of the time constant. And the difference increase with the voltage jump of larger value of the resistor 3. The decrease with the amplitude, the physical length of the Sawtooth produced with the circuit. The electrical length remained the same because the length of the gate was not changed. Resistor 2 has a similar effect of linearity because of the interior of the resistor 3. An example of the decrease in the value of the resistor 2 result of the decrease in linearity of the equation. The number of the time constants equal the gate length of the total time constant. Illustrate the decreasing the resistor time. The time constant is equal to the resistor time. The capacitor total time constant is decrease with the increase of the number of the time constant with the cover. The increase with the linearity. The other the effect of the increase of the jump voltage and the increase of the amplitude physical length of the Sawtooth. Changing the value of the voltage current collector does not affect the linearity. Linearity is dependent on the gate length of the resistor and capacitor. Voltage current collector does affect the amplitude of the waveform value of the jump voltage and has been attained. All right, Chapter 3 summary.